So good afternoon, everybody. I'm Paul Davies with Boeing, based in Southern California in the US. I grew up here, which is why I sound like I do. I'm going to talk a little bit today about how to measure the enterprise impacts of augmented reality. Now, Boeing has a long-standing history in AR. Some of you, I'm sure, will know that one of the first industrial applications that at least I know of came out of Boeing back in 1989 or 1990 by one of our researchers, Tom Cordell and Dave Mizell. And it was up in the Everett wire factory, and we were showing how to route, or they were showing how to route wire harnesses on a wiring board. And it was done with a head-mounted display. It really was quite ahead of its time, both in terms of culture and technology. If you look up some pictures of that device, the display was that the HMD was a monstrosity. It was done under controlled conditions. What you saw on your overlay was very simple, just one line that was indicating where a harness should be routed. So we've come a long way since then. We've been involved pretty much since then, Boeing has, in terms of augmented reality development. And now I lead a team at a Boeing Research and Technology. And we have developed a prototype system that we have supplied our internal customers with, which would be the defense and the commercial business units, our programs. We've put that on the shop floor in a number of places, and we're investigating use cases for it, applications, ergonomic issues, data interface issues. But of course, one of our long-standing desires, just like any company, has been to figure out what's the business impact of this going to be. How much does it cost to develop, and how much does it improve quality, or how much does it reduce cost, and is it worth it? So that's what I'm going to talk about today. So this actually leads quite nicely on from Mark's presentation. Mark was making those big, bold statements. I'm actually going to be able to back up a few of them, talking about improvements in quality, and reduction in time in building and assembling products. So we've looked at what we're trying to do. What would we like out of an AR system? And we've identified these 5 attributes. So I'll run through them one by one. So we're really interested in, of course, in reducing assembly errors. And so I should maybe take a step back and set the stage and say the primary kind of background to today is using AR to provide work instructions to mechanics. So we're trying to improve on delivering 2D drawings or 2D instructions, and do that more immersively using 3D techniques. So if we do that, we expect to have a reduction in the number of assembly errors. And now, in a high value product like a satellite, could be $1 billion with a B dollars or more. One error could become very expensive, and we've had situations like that before. We've seen in the past that a mistake requiring a couple of weeks worth of rework can quickly get very expensive. So if we can save just one error, we can be talking big money. We're interested in reducing training requirements. We want to be able to train our folks faster, more efficiently. And also train them in the more basic assembly skills rather than the specifics of a particular product or a particular task. We want to teach them how to drill holes properly rather than how to drill a hole on a 777. So if we can use augmented reality to kind of complement their basic training, so we'll train them on the basics, we'll use AR to provide the complement, the information they need on top of their basic training, makes our workforce more portable between programs, which is obviously something we're interested in. We want to be able to reduce assembly time so that we can build more airplanes faster with the same workforce. So we've identified that as one of our goals. We want to facilitate an increase in the recall of work instructions, and studies have shown that when somebody learns a task using an augmented technique where their training material is placed into their world rather than reading it off a separate screen or a piece of paper, they're much more likely to remember it faster and remember it more accurately. So we're interested in using AR for training. And of course, like many companies, we're interested in transferring the wealth of information that is in the heads and minds of the mechanics and technicians. Some of it that may not be captured in work instructions anywhere. It's just tribal knowledge that's been built up over the years. And as that workforce retires, we don't want that knowledge walking out the door with them. So we're looking at tech systems to capture that knowledge and communicate that to the incoming workforce. So we believe AR can help with that. Now, all of these things are going to, we believe, lead, and the data I'll present will back up that we can decrease our manufacturing costs and increase the quality of what we build. And that's what we're interested in. So how can we say that? How can we determine that's true? So we did a couple of exercises to that end. One of them was an analytical study. It was just done on data from 4 production builds out of our satellite factory. We took 4 satellites that we built over a period of about 3 years. We did this study in 2013. And we looked at all the non-conformance data for those programs. Now, anytime something gets built where there's a variance of the design, a non-con or an EPAR, as we call it, gets generated and logged. And then we track that EPAR of how long it's open for, what the root cause is, what are the remedies for it, how do we fix it, things like that. So we looked at all the EPAR data for these 4 production builds, and then we went through them all and we reviewed them to determine which ones we felt could have been affected by if we had an AR tool to deliver work instructions. So specifically, we looked at flexible cabling assemblies. Sometimes mechanics have some latitude in terms of exactly where flexibles go. They're not always called out in the drawings. So where a cable was installed and it was up down to the mechanic to make a judgment call and then it caused an interference later, that would be an EPAR that we felt we could have helped with AR. Harness routing, kind of on the same lines. Component location, pan poles and units, waveguides, where they're installed. We felt AR could have a big impact on that. And stay out areas, or even more importantly, stay out volumes. We've done some use cases where we could show a 3D volume of a place where nothing can be installed because it's going to impact the production operation later. For instance, trying to get a unit through a small opening. So we looked at those 4 root causes or types of EPARs, and then we looked at how long they were all open for, what was the impact on the production schedule. We kind of accounted for if 2 were open in parallel. We didn't give that kind of double credit because we were really interested in how long it delayed the program. And so we compared it to the critical path of the satellite. And we came up with a number that unfortunately I can't share, but it was enough to validate what we were doing. And it was a good justification for us to continue along the path of using AR. So that's what we did 2 years ago. But last year, we started in 2014, ended in 2015. We really wanted some more quantitative kind of testing data rather than just an analytical study, because, of course, this study assumed that all the errors that we found, or the EPARs, could have been avoided. And, of course, that's probably not the case. AR won't solve every problem we think it will. So there was a lot of assumptions in this study. So we wanted to get something a bit more substantial. So we worked with Iowa State University over a period of about 9 or 10 months, as I said, starting in 2014. And we designed a study where we would run a controlled study. We would run participants through in order to try and understand more about how people perform and how they learn tasks and how they follow instructions. So we put together this device here. We call it a wing. Of course, it's not a wing. It's just something we created for the study, but it looks somewhat like a wing. And more importantly, it's representative of the tasks that we do on the shop floor. It has a lot of fasteners, spacers, nut plates. There's some cable harnesses that go on there. There's some parts that kind of is not immediately obvious which orientation they go in, that kind of thing. There's a parts bin where all the fasteners were contained and all the consumables. And then all the parts were laid out on a table like you see on the right there. So we ran about 50 people through this study. Most of them were students. They were all somehow related to Iowa State. So a lot of them were students off the campus. Sometimes we got some faculty, or even I think we had a couple of members of the public come in as well. And each member of the study was randomly assigned one mode of instruction to build the wing. And I'll talk about that in a second. We had them all complete a survey before they started and when they finished. We asked them questions like how old they were, what if they were in school, what was their major, any engineering background, technical competencies, things like that, just to get a high-level kind of understanding of who they are. Each person took around 2 hours to complete the process from beginning to end, and we paid them $20 for that time, or Iowa State University paid them $20. These are the 3 modes of instructions that we offered them, or they were assigned. They didn't get to choose. We assigned it to them. So the first group of around 15 people or so, or I'm sorry, not the first, but it was kind of distributed throughout the 50, but the first set of people were assigned a desktop MBI mode of instruction. So it kind of like the picture shows there was a desktop computer in the corner of the room, and the screen was kind of facing away from the assembly, so they couldn't stand at the wing and kind of see the instructions at the same time. And they would have to walk over to it. What was written on the screen was a PDF document. It just had 2D drawings on there. You couldn't rotate them. It was just something you scroll through just to read what the steps were to build the wing. And this is actually most similar to what we do in Boeing for work instructions. Satellite factory and the places in the commercial factories that I've seen, a lot of times they'll see a computer sitting in the corner, and it's for the mechanics to go reference their work instructions and get what they need. The second group were given a tablet computer. It was running Windows, and it had the exact same PDF on it with the 2D instructions. But the only difference is, of course, now they can use that whilst they're stood next to the wing, so they can kind of have it readily accessible to them. The tablet was on an arm, so they didn't have to hold it. So we didn't take out one of their hands by holding it. The arm was on wheels, and it was flexible, so they could kind of move it around as they wanted, and you could position it somewhere, and it'll stay there. And the third group used our prototype, the system that my team put together, the augmented reality system. It's the exact same system that we have on the shop floor that we're doing our pilots with. And that had, of course, 3D immersive animated instructions on how to build the wing. It was essentially the same steps as what's in the PDF, but it was shown in 3D and with animations. Now, when somebody was assigned their mode, they would complete the building of the wing twice. They would actually, first of all, practice on a test assembly, which is something small, not the wing. So everyone went through a test assembly once. So the people who picked up the tablet for the first time, who'd never used AR, were able to at least experience it for 10 minutes before we started their test, and they would build a test assembly. Once they had built the wing, we would take the wing apart again, and we would have them build it using the same mode for a second time. So if you were assigned augmented reality, you would build it using the AR system. We would take it apart, and you would build it again using the AR system for a second time. And we did that because we wanted to understand a little bit about the learning curve of how people learn instructions. So here's a video of one of the participants performing or midway through the task. So we had all these cameras mounted around the room on the right-hand side, and you can see she's wearing that helmet, and that's, I'm going to pause it here for a second. That's so we could track, we had some markers on the helmet, that's so we could track where she was in the room or where the person was in the room, and also where they were looking. Because we were tracking the tablet as well for the augmented reality, we tracked the person's head. We were even able to determine what percentage of time were they looking at the tablet screen, or were they looking at the part or the parts bin or whatever. And we kind of correlated all that data, and we had a lot of interesting plots that showed the percentage of time they spent actually value added, touching the wing, compared to trying to understand instructions or trying to find parts and things like that. That's in a detailed paper that's been published, and I can send that to folks if you're interested. It won't be in today's presentation, but all those details have been published. So let's go back to the video. So she's just completed that first step. You can see that spar being put in on an angle, and now she hits next task on the user interface, and that arrow pops up and shows her that the next task is over in this corner of the room. So she's going to wheel the computer over there, the tablet. And if you look on the left there, it's showing her that she needs to pick up 6 of those fasteners from the top bin and 6 of the probably nuts from the lower bin. And of course, all this time, as she's moving around her head, we're tracking all that. We're understanding where she's looking, like I mentioned. So
the tracking is just for the study, not for the operation.
The tracking of the head is just for us to understand where she's looking. Yeah. So here you see, so now she's got the parts, and now it's showing what to do with them. So she picked up 6 of those fasteners, and they're being installed, and so she wheels it over and completes it. So there's about 45 steps to this. This just shows I think 2 or 3 of the steps here. So let's look at some of what we found. So when we looked at the number of errors that people made, so when they built the wing, we would grade them basically on how many mistakes they made, and whether they caught the mistake, and whether they fixed it, and how long it took to fix it if they did catch it. So as I said, each person built the wing twice. So the first data set is the blue data, and the second time they built it is represented by the green bars. So when we used the desktop PC, out of about 50 steps building the wing, the median number of errors was 8 when the first time someone used a desktop PC. Second time they used it, because they had learned a little bit from the first time, they made fewer errors and it was down to 4. And when we looked at the tablet MBI, which, as a reminder, was the same 2D drawing PDF on the tablet, it was much better, of course, because they were able to look at their instructions. We saw 1 error for the first and second time. It's not showing a learning curve. I'm sure there is one, but of course we only had 2 cycles, so it probably is not enough data to show the learning curve with that. And then when we looked at the augmented reality system, we saw it's actually a half an error mean out of 50 for building the wing, and then the second time nobody made any errors with the AR system. And keep in mind, of course, these are people who probably maybe never heard of augmented reality, probably have very little, if any, experience with it. The system, of course, was a prototype system, was not perfected in terms of user interfaces or anything like that. So we're really comparing, to see results like this is very powerful, I think. We're comparing a new technology that is not perfected and people are unfamiliar with to something like reading a document, of course, which has been around for hundreds of years, whether on paper or more recently on a computer screen. People are much more used to reading, a 2D document. So this was pretty huge for us to see this kind of data here in terms of error reduction. When we looked at the time it took for people to build the wing, we saw a reduction kind of on the same order as the number of errors. The desktop computer, the black line in the center of each chart is the mean. So we're looking at around 35 minutes for the first time somebody built it, and it went down to 20 minutes on the second time. So people got a lot better, of course, not quicker with that. The tablet with the MBI instructions, we were looking at like 30 minutes down to 20 minutes, maybe a little bit less, maybe 19. And on the AR system was the fastest overall. We started out at about 24 minutes and went down to maybe 18 or 19 again. So we did see a reduction, a speed up of the build, but the effect was not as great as the number of errors. Now, I mentioned the attributes that we were looking for. Assembly time and error reduction were 2 of them. They're the kind of 2 of the big hitters. Personally, I feel error reduction is huge for us. Speeding up the assembly is good, but a mistake can quickly erase any gains you've had in the assembly time. But we saw good data in both the errors and the speed. So when we looked at the first time somebody built the wing using the desktop compared to the worst case to the best case, which was the second time somebody built the wing using an augmented reality system, we saw over a 90% improvement in the first time quality when you look at the number of errors. And when we did the same for the time to build the wing, the worst case, we compared it to the best case, it was reduced by over 30%. So these numbers are obviously very exciting and for everyone and huge for us. Even if we only realize a tiny percentage of this, when you compare these to the scale of what we do and other large manufacturers do, we roll approximately 2 brand new commercial airplanes across the programs out of the factory every single day. So the number of operations that have gone into building those 2 planes, I don't even know. But if we can just reduce the number of errors by a small percentage and speed up time by a few percent, it's huge for us. So we're excited to see this data. But at the same time, I don't want everyone to think that no matter what you do, you're going to get a 90% improvement. This was, of course, comparing the best case to the worst case, or the worst case to the best case. So we wanted to understand a little bit more and break this down and see where AR had the highest impact and where it had the lowest impact. And in fact, as you'll see in one of the cases, it actually had a negative impact. And so we'll look at that now. We broke out the time to build the wing by step. So we're looking at each step here in different colors. This is only a small subset of the data. And if we look at step 5, we saw that the time to complete step 5 was actually higher using augmented reality than any of the other modes. And so we were interested in why that was. We wanted to look at what was step 5 and why it was taking longer with AR. And then we looked at, if you look at step 6, it's significantly lower, much more so than comparing the other steps. So there was a big drop off in step 6, so we wanted to look at that also. So we pulled up the data, and it turns out step 5 was that twist step that I showed in the video. It's where that spar comes in and has to kind of go in on a kind of an awkward angle to get it to fit, and then slid into place. Now, we were thinking the AR would be awesome for this because you can show the animation and the sequence of how it goes. But Our downfall here is that we weren't handling the occlusions in AR. So when I say occlusions, I mean real objects occluding virtual objects, if they should. If we have a virtual object being shown here and you put your hand behind it, the virtual object should occlude it. If your hand goes in front, your hand should occlude the virtual object, just the way we see things. Now, the system is capable of doing that, but we had it turned off for the study because a lot of the parts were shown coming up from beneath the wing, like washers and bolts. And of course, if you turn the occlusion handling on, you just don't see those parts. So that was a problem for us. So we turned the occlusion handling off. So as you see here, right where my cursor is, that part of the spar goes underneath the real piece that's already been installed. And some participants misunderstood that step because it shows it going on top and not underneath as it should. So we had a couple of people who tried to mount it on top, and it took them a while to figure out that that's not where it goes. I think when they got a few steps later, there were some other fasteners that go in at the end, and of course they were no longer fit because there's a big gap, and so they had to take it all apart again. So that was causing a problem there. So we learned here that it's very important for what the user sees in their augmented scene to be realistic or what they would see if it was real from their viewpoint. And then step 6 was the one that was particularly good, and we saved a lot of time in step 6, and that was where the task was to put a stack of washers together to act as a spacer. There was, I think it was 4 or 5 washers that had to be stacked up. And my best guess at this, or my feeling, is that this is because stacking washers together is not really intuitive. You would probably think there should be a spacer for that. Why would you stack washers? There should be a pre-designed spacer to fit there. So when people were reading that on the paper document, they would probably maybe question themselves a little bit, maybe wanted to double check what they were doing, make sure they're on the right step, make sure they got the right part from the bin, because it only referenced part numbers, so they would probably check that the washer was the right part number before they did it. Whereas with AR, we were able to show those washers being stacked up. It was very obvious. Of course, it's spatially registered, so there's no confusion about where it goes. I think this just showed us that AR, people believe, people are much more likely to believe what they see and understand what they see faster than if we use other methods. So I think that's all I had today. As I mentioned, this was obviously huge for us. It was the justification that we needed to continue what we're doing to develop the systems and work with our partners. I mentioned we have some pilots on the shop floor. We're looking to further those based on this data. And ultimately, our goal is to get some of this technology streamlined into production in real use cases. So that's it. Thank you.